Ever wondered how the beautiful patterns of a soap bubble or the vibrant colors of a peacock's feather come to life? Intriguing, isn't it? Well, these stunning visuals are not just a play of light and color, but they are the result of some fascinating physics phenomena known as interference and diffraction. In our everyday life, we encounter numerous instances where these phenomena occur. The radiant colors of a CD, the mesmerizing patterns on a soap bubble, the rainbow of colors on a peacock feather, and so much more. All these are the stunning outcomes of interference and diffraction. Now you might be wondering, what exactly are these phenomena? Simply put, interference and diffraction are phenomena that occur when waves interact with each other or with obstacles in their path. Interference happens when two or more waves overlap, while diffraction occurs when waves encounter an obstacle or aperture. The resulting patterns are what we observe as beautiful colors and interesting designs. But why should we care about these phenomena? Well, understanding interference and diffraction is not just about appreciating the beauty around us, it's more than that. These concepts are fundamental to comprehending many technological applications, from the design of optical instruments like microscopes and telescopes, to the workings of our communication systems, and even to the development of cutting-edge technology like quantum computing. Interference and diffraction play a crucial role. So as we dive into the world of interference and diffraction, be prepared to discover the science behind some of the most captivating visuals and unravel the mysteries of wave interactions. It's going to be a journey filled with fascinating insights, equations, and applications that will surely pique your curiosity and broaden your understanding of the world around you. So gear up as we unravel the mysteries of these wave interactions. Stay tuned for the next scene where we'll delve deeper into the concept of interference and explore how it shapes our world in ways you might never have imagined. Imagine two pebbles dropped into a pond. The ripples they create overlap, right? That's interference. A phenomenon that occurs when two or more waves combine to form a new wave pattern. Picture this. You're at a concert, surrounded by a crowd, all vibing to the music. Suddenly the singer hits a high note and you hear a weird echo. That's interference in action, the result of sound waves colliding and melding into a new wave. But let's get a bit more technical. Interference is not just about waves colliding, it's about how these waves add up. This is where the superposition principle comes into play. It's a fundamental concept in physics that states the total wave function of a system of particles is the sum of the individual wave functions. Let's simplify that with a basic equation. Psi total equals psi 1 plus psi 2, and so on up to psi n. In this equation, psi, represented by the Greek letter psi, is the wave function. This wave function describes the wave at each point in space and time. So, when multiple waves meet, their functions, or PS, add up to create the final wave. This is interference in a nutshell. But what about when waves cancel each other out? That's also interference, just of a different kind. We call it destructive interference, and it happens when waves of equal amplitude and opposite phase meet. They cancel each other out, resulting in a flat line. On the other hand, when waves of the same phase meet, they add up to form a wave of greater amplitude. We call this constructive interference. Interference, as simple as adding up the wave amplitudes, plays a significant role in technology. It's how antennas pick up signals, how noise-canceling headphones work, and even how holograms are made. It's a fascinating principle that's all around us. Intriguing, isn't it? Now, you may be wondering where we see interference in our daily lives. Well, interference happens all around us and plays a crucial role in many technologies we use every day. Let's delve into some fascinating examples. Firstly, consider the world of telecommunications. Ever wondered how your cell phone can pick up a call from across the globe? That's the magic of wave interference at work. When you make a call, your voice is converted into an electrical signal, which is then transmitted as radio waves. These waves can interfere with each other, leading to a loss of signal. But by understanding and manipulating interference, engineers can design systems to minimize this loss and ensure your call gets through loud and clear. Next, let's talk about Wi-Fi. Wi-Fi signals are also a form of waves. When these waves encounter obstacles like walls or furniture, they can undergo interference. This can lead to dead zones where the Wi-Fi signal is weak or non-existent. By leveraging the principles of interference, we can design Wi-Fi routers and repeaters to overcome these obstacles and provide strong, reliable internet access throughout our homes or offices. Lastly, let's touch on the realm of audio technology. In a concert hall, sound waves from different instruments can interfere with each other, causing some sounds to be amplified and others to be cancelled out. By understanding interference, sound engineers can design the layout of speakers and the acoustics of the hall to ensure every note reaches the audience just as it's intended. Interference also finds applications in medical imaging, radar technology, and even quantum computing. The list is practically endless. In each of these examples, understanding and harnessing the power of interference can significantly enhance the performance and reliability of these technologies. It allows us to transmit information more efficiently, enjoy better sound quality, and even explore the frontiers of quantum physics. Interference, thus, isn't just about overlapping waves. It's about making our communications clearer and our technologies more advanced. Next, we move on to diffraction. Ever noticed how water waves bend around a stone? That's diffraction. It's a phenomenon that occurs when waves encounter an obstacle or an aperture, causing them to bend and spread out. This bending or deviation is what we call diffraction. Diffraction isn't just limited to water waves. It's a universal phenomenon that can be observed in all types of waves, including sound, light, and even radio waves. What's even more fascinating is that the diffraction pattern, or the way the waves spread out, can be precisely calculated using mathematical principles. Let's dive into the equation that makes this possible. The formula used to calculate the diffraction pattern is lambda equals d times sin of theta. Now that may seem a little overwhelming, so let's break it down. In this equation, lambda represents the wavelength of the wave. The wavelength is the distance between one peak of a wave and the next. It's a fundamental property of a wave that determines many of its characteristics, including the energy it carries. Next, we have d, which stands for the size of the slit or obstacle that the wave is encountering. This could be anything from the width of a gap in a barrier to the size of a stone in a stream. Finally, we have theta, which represents the angle of diffraction. This is the angle between the direction of the incoming wave and the direction in which it is diffracted after encountering the obstacle. By understanding this equation, we can predict how a wave will behave when it encounters an obstacle or aperture. This knowledge is crucial in many fields of technology, from designing optical systems to improving wireless communication. So there you have it. Diffraction, a simple bending of waves, can predict complex wave patterns. Fascinating, isn't it? Like interference, diffraction too has a significant role in our daily lives. It's a phenomenon that's instrumental in various technologies we use every day. Let's take a look at some of them. First up, optical systems. Diffraction is the principle behind the function of lenses, microscopes, and telescopes. It's the bending of light that allows these devices to focus and magnify, making it possible for us to see distant stars or tiny cells. Next, we have wireless communication. Ever wondered how radio and television signals reach your devices? That's diffraction at work again. These signals are essentially waves that bend around buildings and other obstacles to reach your antennas. Understanding diffraction and applying its principles can greatly improve these technologies. For instance, scientists use knowledge about diffraction to design better lenses and improve signal reception. Diffraction, thus, is not just a simple bending of waves. It's about making our vision clearer and our connections stronger. So that was our journey through the captivating realm of interference and diffraction. We've taken a deep dive into the mathematical intricacies behind these fascinating phenomena. We've seen how interference, the overlapping of waves, is governed by the superposition principle, and how diffraction patterns are shaped when waves meet obstacles or apertures. Just as importantly, we've explored how these concepts are not just theoretical curiosities, but underpin much of our modern technology. From signal processing to optical systems, understanding interference and diffraction is crucial to navigating the technological landscape around us. As we wrap up, remember that these phenomena are not confined to textbooks. They're all around us, in the ripples of a pond, the colors in a soap bubble, and the wireless signals that connect our devices. Remember, every ripple in a pond and every ray of light holds a universe of knowledge. Keep exploring, and until next time, this is D_Quantist signing off.